So similar to the last type of examples we just did, there's sort of a more general version of that I want to at least do a couple examples of. And that is an integral of the form sine to the mx cosine to the nx dx. All right? So these integrals actually work precisely the same way as the integrals we just did in the last video, right? As long as, so if at least one of m or n is odd, we just pull off one copy of that function, sine or cosine, and do the substitution. So I'll say pull out one copy of that function. That's not an f, is it? That function. And do a u substitution. Right? So for example, let's say we had something like sine squared of x cosine cubed of x dx. Right? Let's say we had something like this. All right? So here, cosine has the odd power, so what we're going to do is do sine squared x. We're going to pull off one copy of the cosine and write it like this. All right? Now what we need to do, the way we make that substitution is, since this is the thing we pull out, all of these need to be in terms of the opposite trig function. So since this is a cosine, these two have to all be converted to sines. Now, of course, here we already have sine, so no big deal. We just need to convert that cosine part. So this is sine squared of x, 1 minus sine squared of x, times cosine of x dx. Right, so we do the usual substitution here now. Since all of these are sines, that's what we're going to make our u. Du is going to be cosine x. Okay? And so now we just now we just do our substitution. And this will give you u squared 1 minus u squared du. Right? So that's u squared minus u to the fourth du. All right? And now we can finish that off. Right, so 1/3 u cubed minus 1/5 u to the fifth plus c. So that's 1/3 sine cubed minus 1/5 cosine cubed, or cosine, sorry. Why am I saying cosine? Sine to the fifth plus c. All right. So that's kind of the prototype of how you deal with these. If they're, if both powers are odd, then you sort of have your choice of which one you want to pull out and change. Again, it's completely up to you. If they're both even, then our previous examples also provide the prototype of how to deal with that. Right? So let's do one like, oops. All right, so this computation is going to look quite familiar. Let's say, just to keep life simple here, let's look at sine squared x, cosine squared x. All right? So if both powers are even, we have to rely on those trig identities from earlier, right? Because if both powers are even, there's no way to sort of pull out one extra copy of the function. So when we're here, what we have to do is just say, all right, well, sine squared is 1 minus cosine 2x over 2. Cosine is 1 plus cosine 2x over 2. Right? And now we just multiply that out. So the nice thing, though, about having a sine and a cosine with even powers like this is when we multiply that out, it's going to be a little bit simpler than just like sine to the 4th. So I'm going to pull out both of those 2's as a 1/4 like before. When you multiply this, you're going to get 1 minus cosine squared 2x. And again, just like before, we can't exactly integrate cosine squared, so we have to use that identity. 1 minus 1 plus cosine, since that's 2x, this becomes 4x. Right? Right? Simplify this. We're going to have 1/2 minus 1/2 cosine 4x dx. Right? So now I'm going to pull out that 1/2 to make life easy. Integrate this, we're going to get our x minus 1/4 sine 4x plus c. And there we go. And that's it. And, to deal with this with higher powers, higher even powers, if they're all even, like this is a 4 and this is a 4, then you're going to have this squared and this squared. And so you'll just have to multiply those out, expand them. And again, anytime you get higher powers like this, just keep using those reduction formulas that we talked about at the beginning of the last video. These two right here. These two are quite essential for dealing with even powers like that.